Hello and welcome to this video. My name is Aniruddha, call sign is Victor Uniform number 3 Foxtrot Mike Lima. In this video, we are going to design a simple 2-meter VHF ground plane antenna for the amateur radio bands. And for that, we are going to use MMANA-GAL software. We are going to use a basic version for it. I will put the download link in the description below. It's a free software. At least the basic version. You can go and download it and install it and use it freely. There is a page for documentation as well, which you can read. Let me quickly open up the software and we'll start designing this antenna. Okay, so as soon as you open this software, you will be greeted with this page. Here you can see there are 4 tabs: geometry, view, calculate, and far field plots. We'll see each one of them as we go on. Let's first see the geometry tab. Here we can enter the name for the antenna. I'm going to write 2 meters VHF ground plane. You can enter anything that you like. Now in India, the VHF 2 meter amateur radio band is between 144 megahertz and 146 megahertz. So I'm going to enter the frequency as 145 megahertz. That's at the center of this amateur radio band. So we are done for this page. Now, the other things on this page will come to know as we proceed. For the time being, we are going to draw this particular antenna, and for that we have to go to this particular section. We have to press this button called as wire edits, and we are going to select the XZ plane first to start drawing. Now the ground plane antenna will have a vertical radiating element which will be a quarter wavelength. So for 2 meters it would be approximately 0.5 meters. We'll be starting with 0.5 and we will fine tune it as we go along. And it will also have 4 ground plane elements, which would be at an angle of 45 degrees with the horizontal as well as with the vertical. So let's start drawing. We have selected the XZ plane and we are going to press this button called as the new wire, and we are going to just draw a vertical element. Now the software has given this element as name as wire number 1 and the length is 1 meter. We want it to be 0.5 meters, so you can easily right click on it, go to wire definition, and you can select the length of 0.5 meters. Okay, we have to make sure that the start point is selected so that it will keep the start point as it is and change the length on the other side. So I press OK, and now this length is 0.5 meters. We have drawn the vertical element and now we want to draw the ground planes. So I draw a ground plane element at 45 degrees with the horizontal axis as well as the vertical axis. The length is 0.7. We want it to be 0.5. So I do that here in wire definition, 0.5. I've kept the starting point as it is and pressing OK. Similar way we do the ground plane element here. Similar way, 2.5, and starting point is kept as it is. Okay. So we have drawn 2 of the 4 ground plane elements, and to draw the other 2 remaining ground plane elements, we will go to the plane YZ and do the same way. Draw the ground plane element at 45 degrees, enter 0.5, keep starting point, press OK, and here as well. All right, so we have drawn the antenna, and we can go and press OK. And now we go to the second tab called as view. Okay, before we do that, we see the different coordinates of the wire elements that we had drawn earlier. And now if we go to the view, you can see your antenna in 3D. You can drag the mouse and see your antenna from all sides. Okay, so here we see the vertical element and 4 ground plane elements at 45 degrees. The length of each of these elements is 0.5, which you can see here. I think let me shift myself. Okay, so here you can see the wire length elements by selecting the wire element. So if I select this is wire number 1 and 0.5. Okay, so now once we have drawn the antenna, now we need to introduce a feed point to it. Now for this ground plane antenna, the feed point is here, beginning of the vertical element. So beginning of wire number 1. Okay, so how do we do that? We go to the geometry tab. Under sources, we enter wire 1 beginning W1B, Whiskey 1 Bravo. Okay, wire 1 beginning, and press enter. And now if you go to the view, you can see a small circle where the feed point is. And that's nothing but the source you see here, right? So we have introduced a feed point as well. Okay, now it's time to see how this antenna would perform under different conditions. And we'll come to know if the lengths of the elements are what they're supposed to be. Okay, so let's go to the third tab called as calculate. Here we are going to keep the frequency as 145 megahertz. That's what we want. Here we're going to keep the ground as real. Okay, and under ground setup, make sure that this checkbox is unchecked. So if you check this, it's going to consider these many number of radials for the antenna. Here we have already drawn the 4 ground plane elements, so we do not want any additional wire radials to be considered. So we are going to uncheck it, but it's okay. The other part I will explain in the following videos because it doesn't concern right now. Here we are just going to keep the default values. Okay, here you can add the height to the antenna. How high is the antenna? I'm going to be a little realistic. I can put an antenna up to 5 meters, and the material I would be choosing would be aluminum pipe. That's what I'm going to use to make that antenna. If you want to use copper, you can select copper pipe. Okay, now with 145 megahertz with real ground with 5 meters height and aluminum pipe, we have designed this antenna, and we are going to press start to see its performance. So here you see this is the impedance. The resistance part is 57.3 ohms. Reactance part is 18.14 ohms. SWR is 1.44 and a gain of 5.2 at elevation of 5.1 degrees. Okay, not bad. We can go and check here at plots. Okay, we can go to the SWR and press resonance. Okay, here we see that the lowest SWR is at 141.338. Okay, and if we see that same thing here, 141.338, here you see the reactance part is 0, which means it's resonant at 141.338 with SWR of perfect 1. But that's not what we want. We don't want it to be resonant at 141.338. We want it to be resonant at 145. But since it's resonant at a lower frequency than what we want, it means that probably the wire lengths, the element lengths are a little too long, and we need to shorten them to bring this resonant point to 145 megahertz. We don't have to do anything manually in this software. Okay, so let's see how we can shift this point to 145 megahertz. Now we know that it is resonant at 141.338. So we go to the geometry tab and put that here, 141.338. Okay. And then go and calculate it one more time. And surely enough, it shows the same result over here. Okay. Now, what we can do is we can go to the button over here, which is called wire scale. Okay. And we can enter the new frequency as 145. That's what we want. As soon as we enter 145, it has given a multiplying factor of 0.97, which would be applied to all the elements in XYZ plane to bring that resonant frequency from old frequency of 141.338 to the new frequency of 145 megahertz, which we want. I'm going to press OK. And now if you go and check in the view, I will again move myself. And if you click the vertical element, earlier it was 0.5. The software scaled it to 0.487 to bring that resonant point from 141 to 145 megahertz. Similarly, if you select any of the ground planes, you'll see that the length has been reduced. Okay, so the software has done its work. Now, if you go to calculate and if you enter 145 over here and press start, now you can see at 145, you are perfectly resonant with a resistance of 52, reactance of 0.5, near 0, and SWR of 1. Now, you can go to the fourth tab, which is called as the far field plots. And here you see the radiation pattern of this particular antenna. So this is the bird's eye view. We are viewing the antenna from up above. So this is the Z axis right over here. And this is the X and this is the Y axis. Okay. So if you look from the top, you will see the radiation pattern like this, which shows that it is an omnidirectional antenna. And on the right hand side, you see another pattern. So if you cut this sphere in half and look at it from this side, you're going to see this radiation pattern. Here, you can see that this particular lobe over here is having the highest gain. And if I click on that, I can see here that at an elevation angle of 5 degrees, you can see the gain of 5.2 dBi, which is the highest gain. How do we know that? Because here we see the maximum gain minus the gain shown at this particular point is 0, which means this is the maximum gain in this particular plot. So 5 degrees, which is a very low elevation angle, and a gain of 5.2 dBi, which is quite good for this antenna. So that's how you can see the radiation pattern. Okay, let's just do one thing. Let's just save this particular plot, far field plot, save far field plot, and I'm just going to say 2 meters with 5 meter height, right? I'm going to save it. We'll come to know in a minute why. But if this is not clear enough, if you're not able to imagine this, you can go to 3DFF. Okay, and press OK over here. And now it will draw a 3D figure of the same. So if you looked from the top, it's going to show you omnidirectional radiation pattern. And if you look from the x-axis, so that was the graph plot on the right. So you can see this is the point of maximum gain. So this way you can see the radiation pattern of the antenna that you have designed. Okay, now let's do one thing. Let's change something and see how it affects the antenna. For example, we go to calculate again, and instead of 5 meters, let's select 10 meters from the ground. Okay, so we have increased the length of this particular antenna. They say that height is might. So let's see. So let's go and start this simulation with 10 meters of height. Okay. And now you see here you will say that it's just the same, nothing has changed much. Okay, but that's not the case. If you go to the gain tab, here you see earlier when it was 5 meters, it was 5.1 dBi, and here you can see that it has increased to 6.38. But not just that, look at the elevation. The maximum gain of 5.19 was at 5.1 degrees elevation angle, which has reduced to 2.7, which is great. So higher gain at a lower elevation angle, which means this antenna is going to reach places, okay, long distances. Again, we go to the plots, okay, SWR resonance, and it's going to show that it is resonant at 145, which can be seen here as well. Anyways, so let's go to far field plots, and this is how it looks. So here, if I click here, you can see it is 6.4 at 3 degrees. It's quite good. We can actually save this far field plot as well. I'm going to name it 2 meters at height of 10 meters. Okay. And now we have saved both the radiation patterns. Okay. Far field plots. What we can do is we can actually compare the two. So I'm going to go to tools and compare. Let me just change the color for this to blue. Okay. So the one at 10 meter height is blue in color. Okay. Let's just remember that. And I will open the other one, which was at 5 meters, which is red in color. And now you can clearly see as we increase the height, the gain has increased in all the directions. If we look from the top, and here also we can see that the one which was at 10 meters is showing a higher gain at lower angle as compared to the antenna which was at 5 meters of height. So this way you can compare different things using this software, and you get a good understanding of the antenna. So I'm going to make a series of videos, at least I'm going to try, and we'll introduce different antennas and we'll see different features of this software which we have not seen in this video. So if you liked this content, if you want to explore more, please consider subscribing to this channel. It gives me great motivation to come up with videos like this. So until then, 73 is to you. This is Victor Uniform 3 Foxtrot Mike Lima.